Hello everyone, thank you for listening to my talk, Exploring and Exploiting the SQLite, Finding More Bugs by Targeted Fuzzy. My name is Wenxiang Qian and I am a security researcher of Tencent Blade team. I work in fields of web browser and IoT, and recently I am working on security of virtualization. Those cloud things. And then let me introduce my team. The Tencent Blade team was founded in 2017, and we are focusing on security research in the fields of AIoT, mobile devices, cloud virtualization, blockchain, and so on. And we have found many vulnerabilities and have reported them to their vendors. And here is the outline of my talk today. And first, I will present an overview of the vulnerabilities and the findings of the father. And then the background about the previous research and why we choose this target. And a simple introduction of strategies of manual auditing the code in case you are wondering how we found these vulnerabilities. And then the implementation of the father, the design concept, and how we exploited them in TEF Cup 2019. And last, a bit concluding remarks. In November 2018, we discovered 5 vulnerabilities in SQLite together called Magellan. And since then, many new protective measures have been introduced into SQLite, especially WebCircle, because of Magellan that we have reported to Google. And this year, we have found many bugs in SQLite too, and especially in FTS3 and FTS4 extensions. 3 of them can chain together. The first one, the 13750, this one can bypass the defense in depth. And the following 2 to cause remote code execution in Chrome through WebCircle, or any binary built with SQLite, enable FTS3 and allow external circle queries to be run. And the vulnerabilities are discovered through both manual auditing and fuzzing. And after we reported all the vulnerabilities to Google and SQLite, we also committed our father to Google and named SQLite 3 Shadow Table Father, and it is now running under Classic Fuzz. I can tell you that this one has found many bugs. It has found 6 more new vulnerabilities or bugs in the first week and many more in the following weeks. And here is a list of the bugs it has discovered. Let's continue. You might be curious about why we choose FTS3 again to audit, and here is why. The first, it is complicated enough, and the FTS3 is created in the form of virtual table, but every FTS table has additional 3 to 5 real tables called shadow tables. They are related to each other. And then comes the oldie and goodie SQLite. It can be reached from the remote. Chrome or any browser or apps that is using Chromium can be reached through the WebCircle. Also, there can be some attack surface in other places, such as the server with something like PHP with SQLite, and if they support FTS3 and accept remote queries, they could also be affected. Also, it is very old, and here's a snapshot showing the first few lines of FTS3.c file. It says that it was written from almost 14 years ago. and compares to the standard queries that are often well tested by others, and FTS is included but intermingled with lots of standard queries. It is harder to reach. For example, Google's father, so it is expected that it is less tested. Last year, we had a talk in another conference in China, and that talk about how we audited the lexical parser, especially lex and YCC-like parsers. The lemon parser used by SQLite is very alike to the function of Bison and YCC, and you can see the lemon parser has introduced a security model along its development. Also, based on what we have researched on SQLite's parser, we found that it is not likely to have severe bugs, although there can be some minor bugs, for example, null pointer dereferencing or divided by zero exceptions. But this conclusion was done several months ago, and things could change. If you have limited time to audit the code of SQLite, I suggest you can put less effort in auditing this part. Also, we didn't analyze the lemon parser itself, but only the parser code in SQLite. We also have a link to the text version of our previous researches. Yet we don't have an English version, but for your reference, you can just right-click on the web page and translate it into English. The result looks good to me. Yeah, and thanks to the Google and kudos to the machine translation. So then let's talk about the blobs. Complicated components like FTS need to store data in a binary tree and query data from the tree. The easiest way to do this is to store the data in a blob and convert it into a binary tree when needed. The blobs are objects for serialized, deserialized use. I should point out that it's not only in SQLite. If you have noticed any software doing some deserialized stuff, I was talking about converting binary to objects. You may know this often causes problems. The blobs will be eventually represented by real objects. Since SQLite is a C program, the objects are often structures with different types of members. Besides the strings, integers are very common in a structure that controls the code flow. The integer overflow is also common and somehow very hard for developers to find. Even a software with code review may also suffer from this type of bug. Also the signed bit. When it comes to the integer, many often have signed unsigned cast and can potentially cause problems. Also, there are some functions like the realloc. And have they remembered to zero out all the memory allocated? And are the arguments passed to those functions legal? For example, if the code is malloc quote integer minus a constant number, have they tested if the integer is really bigger than the constant number? If you didn't initialize the memory and return them to the user, they can be used to leak raw heap data. This will let an attacker to bypass the ASLR. And here too, former realloc related vulnerabilities in SQLite. Then I think we should always pay attention to some functions that is not designed for daily use, such as performance tracing, debugging, logging. All those functions, they provide external API-like calls, but they are not even listed on the wiki. People barely know their existence, so that is evil, obviously, because that often means they are lack of testing. For example, spatial insert operators can be used to issue commands to FTS3 and FTS4 tables. Even every FTS3 and FTS4 has a hidden read-only column which is the same name as the table itself. So inserts into this hidden column are interpreted as the commands to the FTS3 or 4 table. Okay, let's choose some interesting commands. The optimize command causes FTS3 or 4 to merge together all of its inverted index B trees into one large and complete B tree. Doing an optimize will make subsequent queries run faster since there are fewer B trees to search, and it may reduce disk usage. And the merge equal xy command, where xy are the integers, cause SQLite to do a limited amount of work toward merging the various inverted index B trees of an FTS3 or 4 table together into one large B tree. The x value is the target number of blocks to be merged, and y is the minimum number of B tree segments on a level required before merging will be applied to that level. See, these simple operations are doing a lot of logic, and many of them can trigger problems when the database is modified by an attacker. And the last one, make a father before auditing any code. It can give you an extra manpower, and sometimes will surprisingly find some interesting problems for you. In case you haven't heard of shadow tables, I will explain it here. The FTS3 virtual table implementation make use of real, which is non-virtual database tables to store content. For example, when the content is inserted into the FTS3 virtual table and the data is ultimately stored in real tables named content, segdir, segments, stage, and doc size. These auxiliary real tables that store content for a virtual table are called shadow tables. The leftmost column of the content table is an integer primary key field named doc ID. Following this one, column for each column of the FTS virtual table as declared by the user and named by prepending the column name supplied by the user with C and the index of the column within the table, numbered from left to right starting with 0. And the state and the doc size tables are only created if the FTS table uses FTS4 module, not FTS3. And for each row in the FTS table, the doc size table contains a corresponding row with the same doc ID value. The size field contains a blob consisting of many FTS variants. Each variant in the size blob is the number of tokens in the corresponding column of associated row in the FTS table. The state table always contains a single row with the ID column set to 0, and the value column contains a blob consisting of one more FTS variants, where this is again the number of user-defined columns in the FTS table. The first variant in the blob is set to the total number of rows in the FTS table, and the second and the subsequent variants contains the total number of tokens stored in the corresponding column for all rows of the FTS table. And the two remaining tables, the segments and the segdir, are used to store the full text index. Yeah. And here's the concept of the structure-aware fuzzing. Let's use Google's introduction directly. The first, generation-based fathers usually target a single input type, generating inputs according to a predefined grammar. And coverage-guided mutation-based fathers, such as libfather or AFL, are not restricted to a single input type and do not require grammar definitions. So mutation-based fathers are generally easier to set up and use than their generation-based counterparts. But one thing, the lack of an input grammar can also be a disadvantage. It can also result inefficient fuzzing for complicated input types, where any traditional mutation like bit flipping, they can lead to an invalid input which is rejected by the target API in the early stage of parsing. With some additional effort, however, that fuzz can be turned into a grammar-aware, structure-aware fuzzing engine for a specific input type. Because SQLite, of course, uses a highly structured text-based SQL language, it is a good candidate for structure-aware fuzzing. And it has a very good description of the language it consumes. So the Google's fuzzer will first convert this grammar into the protobuf format and translate them with rules to standard SQL queries. And I pasted all the links here. You can go visit them for the further information. So let's begin from making my fuzzer. We can see the class fuzz are contributing many discoveries and improve the security level a lot, but individual researchers usually don't have that many computers. So an important way to find security problems quickly is to optimize the fuzzing code. Google has put forward an idea. The structure-aware fuzzing. This kind of fuzzer can be very useful for a program that has to go through syntax patterns first. Our fuzzer is also based on this idea, but it has made some improvements so that we can fuzz effectively with less power and less price. Also, the effect of fuzzing is always proportional to the amount of code in fuzzing that made a writer fuzzer is as hard as writing a good project. If we do not continue to iterate over the fuzzer, it will be harder for it to discover new problems. And we committed our fuzzer to the Google, and here's a link to it. It's now running on the Cluster Fuzz, and you can also run it on your computer too, and it can be really easily ported to an FTS4 or even FTS5 fuzzer if you wish. I didn't test FTS4 or 5 since Chrome doesn't use them. The basic idea of developing the fuzzers are, first, we should make the data tables available before fuzzing it. Compared to normal fuzzer, this could save a lot of tries. And we should create a table in this sequence. First, FTS3 table F with column A, B, and the shadow table F doc size and shadow table F state. This were used by the FTS4, but we just try to find some code passes of FTS3, which will accidentally go across these two shadow tables. Then we will try to mess up the data tables with queries to table F. This is another different point compared to other fuzzers. We only focus one table, and we don't need to fuzz a lot of FTS tables at a time, and this can also make our fuzzing more effectively. And here comes the differences from the Google's fuzzer. This one is a focused fuzzer. We fuzz only FTS3 and FTS4 part. I believe the Google's fuzzer had already covered the normal queries very well. Also, because we are not making a common use fuzzer with a small set of testing targets. we can make a smaller bytecode set and reduce the complexity of our file. And we can use the file data more effectively. And it targets to only a few complex functions, but not the full SQLite. Yes, we know there are many complex clauses like join, unite, but FTS3 didn't have special rules in processing them, so you don't really need to include them to your file code. We target only select, update, delete, insert verbs. The FTS have many special logics related to these clauses. And an important thing is our father knows the shadow tables. We restricted the table name to F and which have two fixed columns A and B, and so we can know all the name of each shadow tables. In other words, we are only changing the data within those tables and try to see what will happen. And the father will modify shadow tables and try to query or delete or do something to FTS table after finishing modifying the shadow tables. Usually, a father tends to mutate the input with some types of binary data, but not at a whole word. Even you can specify the dictionary. Sometimes the father will still try to change inside a word. And SQL query is very sensitive in the syntax. Failure in the lexical parsing stage could make the father do a lot of invalid tries. And as we talked before, but only a few minor bugs were found in finding the lexical things, so I think there's no need to focus on them first. We can define some shorter bytecodes to represent correct words. The bottom left figure shows that without a dictionary, the mutating can be really painful. The words are broken and generating many invalid tries. The bottom right figure shows an example of encoding of a fuzzy engine. We can use this to reduce the length of text, like select from to only 2 bytes, which is faster and more accurate. Since we have the bytecode in mind, now it's time to design it. We know that the bits are the smallest unit when the father is mutating its input. The main objective of designing is to make use of every bit to make the test case shorter. Just for illustration purpose, here's a very simple example that we use to design a query. The actual bytecode we used is 16 bits long, which is too long to show here. I will introduce a real file later, and you can also refer to the source code for the actual case we have submitted. Now let's go back to this simple illustration. The highest 3 bits represent the verb. Let's call it the verb selector. For example, 000 is to insert, 001 is update, and 010 is to insert. And the lowest 3 bits represent the table to perform the actions. Let's call it the table selector. Usually we have 6 different tables. They are segdir, content, dot size, segment state, and the direct operation on table F. And as shown on the figure, these 3 bits can represent 8 different tables because the value is from 0 to 7. So it is enough to cover every table here. The following 2 bits are related to the table selector. When verb and table are selected, the meaning of this part is then confirmed. For example, the figure shows we are performing an insert operation on doc size table, and the extra type selector is indicated as 01, a short integer type. And the 01 indicates that the numbers are generated as a short integer, which causes 2 bytes. So the father will read the following 2 bytes as the data of both sides. And then they putting all this father stuff together. The father will finally generate this query using 3 bytes. Insert into f.size values 0x123. Okay, after you have defined all the logic of fuzzing, here's another tip to make your coding work easier. Sometimes we need raw data from the mutate engine, such as raw strings, integers, and other simple types. We can also define a raw byte code to represent a symbol type. For example, you can define FF with length and length bytes of raw data. When translating raw string, you can also use the X notation to avoid all the annoying encoding problems like apostrophe and double quotation marks. And here is an example of the corpus generated by the father. And this is also the first vulnerability found by this father. And the test case is only 10 bytes after minimize. The first 2 queries are directly creating an FTS table and set an extra state shadow tables to it. And the following 2 queries were generated from 10-byte shellcodes. And after translation, 4 readable queries will be run in the SQLite. I didn't post the bytecode here because I have updated the father several times and the definition of some bytes has already changed. But don't worry, let me introduce how it was translated. Okay, first some background things. The father is based on the live father, so its entrance is LLVM father test 1 input, and you can easily port it into FLFuzz-based father. And to cooperate with Google's coding practice, the father is using Google's data provider. If you have never read the related code, and here's a simple tip. And in my father, I only used 2 functions from it. They are first, consume integral. This function allows you to specify a type and it will read corresponding bytes from the fuzz input. And the second, consume integral in range, which almost same as above. It can limit the range of the value. In this example, the return value will be no greater than 7 and no smaller than 0. To simplify the test, we disable the defense in depth in our father. This can be easily done with calling SQLite 3 dbconfig with SQLite dbconfig defensive set to 0. But this also means if you find some vulnerabilities in FTS3's shadow tables and you want to exploit them in the Chrome, you should find some ways to bypass the defense in depth first, because it is enabled by default in Chrome. And when you started fuzzing, the first thing to do is always clean up the environment, drop everything that may interrupt the test. And then we will create the table F and its corresponding shadow tables, as we have mentioned before. I have updated the file several times, and one of the new functions I have added is tokenizer, you will see. The father is try to read a byte from a data provider and then select different tokenizer. An FTS tokenizer is a set of rules for extracting terms from a document or basic FTS full text query, unless a specific tokenizer is specified as a part of the create virtual table statement used to create the FTS table. The default tokenizer simple is used. The tokenizer often used with match operation. Different tokenizer can have different match rules. For example, the Porter will reduce a word by the Porter-Steamer algorithm. It can match different words. For example, if you try to match a word ported in a text, it can also match the word port because they have the same prefix. But this is not the key point of our father, so today I will jump over this part and show you how the father processes the bytecodes. The father we used defined a struct used 2 bytes. As you can see, the first 4 bits are the operation type, and we use this value to select which table to operate, and the following 4 bits are the column operation indicator again. We use this to select which column to perform operations. This value is related with the OP type. And then the 4 bits of circle operation. This is a verb selector and the last 4 bits of select operators. The select operators are usually not used except for the condition of operating directly on table F. It's obvious that you will get dizzy now. Let's simulate the running of the father to know how it worked. Please remember, not all members will be used in some situation. Here I will show you a simple translation that will use only OP type and OP circle operation. Okay, let's take this example to see how the father translates OP code to queries. First, the father should read 2 bytes from the data provider, for example, for F21, and then treat the 2 bytes as struct OP data 16, and their binary value is shown in the figure. Okay, let's put them in the struct, and the value of each member is now clear. Okay, you don't need to remember this. Let's continue to move to the code processing part. There are 5 valid OP types representing 5 different shadow tables. The segdir is 0, a content is 1, and so on. The value from 5 to 7 is reserved for further use. Now it's used to represent the table F itself. The OP type is 4, so we know it is K-state. Now the column OP is related with the shadow table state. Because the shadow table state has only 2 columns, so the operation can only perform on one of its columns. Here we select with the result of column OP mode 2. The result is 1, so we selected the column ID as target, and now its data type is K short number. Then it's time for the OP circle operation. This 4 bits member decides the action to be taken on selected table and columns. The shadow table, segdir, and content has different column types, so they should be treated separately here. And other shadow tables has the same type. The first one is a number, and the second column is a block. They are the same, but just by coincidence. The definition of each shadow tables are listed in the left, and the content shadow table is most special, and it has 1 more column than the FTS4 table. But since we have fixed the definition of table F, and the table F have 2 columns, so F contents will be 3 columns. Yes, one column more than the original table. So which is the first one, book ID and C0A, C0B, corresponding with table F's column A and B. Okay, let's back to the shadow table state. Because it has 2 columns, so here we will call getValueByType 2 times and generate SQL queries from the data provider. The function named getValueByType basically reads the bytes from the data provider based on types. If the value is a short number, this one will read 1 byte from the data provider and put it into the output stream. Based on my test, the result of using uint8 and uint16 has no significant difference. So to make the input shorter, I choose to read only 1 byte from the data provider. You can make this longer if you want. Also, I treat the string the same as blob because most of the time they are almost the same. If the value is a blob or a string, first we can read a uint16 from a data provider and read as many as the length bytes of data again from the data provider. After the SQL query is generated, and we call run SQL query to run it. And if there's still some data in the data provider, do all of these steps again until there is nothing left in the provider. And this is how the file runs. And it may sound complicated, but please believe me, if you debug it yourself, you will soon understand how it runs. And hope you can find more bugs using the structure-aware files. And 2 years ago, when we first tried to exploit WebSQL, there was no protection on modifying the shadow tables. This means that we can modify the shadow tables that SQLite use to store real data for full-text search queries. But after that, defense in depth is introduced to Chrome, so that means even you have some vulnerabilities after boil the midnight oil, that doesn't mean you can exploit them on the Chromium because it enables defense in depth. This technology is intended to prevent all modification to its shadow tables. But by analyzing the patch of their last commit on this part, we can see that they only disabled delete, update, and insert on shadow tables. Seems like verbs like create, drop, and alter is not included here. When you notice this, you know Google Spark Bounty is waving its hands to you. If you have read the code of how SQLite creates a FTS3 table, you will realize all its shadow tables are just created with normal create clause. So if we drop their table and recreate the same table, what will happen? Nothing, because it is using select on them when trying to obtain blob data from those shadow tables. In other words, SQLite never sees them as special tables. It's not represented as some kinds of table objects. They are just treated as a normal table. So we can create some fake shadow tables and write malicious data into the fake tables that drop the legal shadow table of an FTS table. Then we can alter these fake tables to the same shadow table name with a FTS table that was used by an FTS table. We change them slinkly and everything works fine. And here is another vulnerability that was found during manual auditing. We are very curious about the realloc since usually every program each has relations to many memory problems. Specifically, in some programs that don't check this that doesn't check the return value very well. Also, realloc doesn't automatically set the reallocated memory to 0, which means if something like a structure with function pointers or pointers to static or global variables were stored in the memory, after the structure is freed, realloc may allocate new memory at that position. Without initialized memory, we can get the old pointers that was stored in it. Here, the function tries to double the buffer z term each time without setting it to 0. The only way to initialize it is a memory copy. It will copy data from the blob to the buffer starting at n prefix, but n prefix is controllable, which means that we can control where it starts to copy data and make it jumps off some uninitialized bytes. And after the operation is done, the uninitialized bytes we have jumped will stay in the blob and will be written back to the database. So we can read from the database again and get those uninitialized data with a single select SQL query. Okay. Now we have a primitive which can leak bytes, and it's almost like most likely to let us bypass the ASLR. And what's next? Yeah, usually a memory corruption. Here we can see the code is converting a signed char to an integer. What's the problem here? First, a root is raw blob data, which we can use the defensive depth pass and control its value. And then when C casts a smaller value to the bigger, it will keep its signed bit. So if we set the A root with index 0 to a negative number, which is from 0x7f to 0xff, we can get an integer with the same value. Next, the code will use the negative integer as index to get an object, not writer. Obviously, it is reading out of bounds. And then the code will try to obtain block.a from the OOB object as target to memory copy. And other parameters, a root and n root are all controllable. A root is a raw blob, you already know it. And n root is the length of the raw blob a root. Yeah. So if we can place a fake object before the real node writer, we can control all parameters of memory copy. But first, we need to find a way to place our fake objects. By reading the code, we know that node writers are created along with increment writer object, which is a variable p writer in the figure. It just looks like the heap data before increment writer is occupable, because we can move the code into the Visual Studio, and here's a trick to monitor the heap allocation and deallocation. You can use the heap snapshot of Visual Studio. Capture the heap snapshot for 2 times. We can know how the heap is used and the call stack when the program tries to operate on the heap. And also the most important thing, what is ahead of increment writer and what's its size? After we know that, so we can do heap function to put our fake objects into that position. And don't forget, we can move the pointer to very front of it because the size of node writer is pretty big. So we can find somewhere which is empty and use APIs from SQLite to put our fake objects there. After we have write what were primitive, where can we write to? Normally, to exploit SQLite, SQLite 3 config will be a good place to write to. It's not only because it is a big global variable, and it's also because SQLite will refer to this variable to know which memory allocation function to call, because it has many function pointers inside it. Usually after memory corruption, the status of program will be very unstable, but this gives us a chance. We can disable all memory operations such as malloc, realloc, free, and we can just simply change their function pointers to not all our rope gadgets. First, we can override SQLite 3 methods.xFree to a function of nothing to prevent any method from freeing the memory. Because after the write version where memory copy, the code will mess up the whole heap and try to free an address from the center of our fake objects, which will make an instant zigzag of our program. By overwriting free, we can let the program run smoothly without trying to operate on the heap. Then overwrite realloc to the first rope gadget. When realloc is called, our shellcode will run. And leave other function pointers as is. No need to overwrite malloc because we will need it later. And here is a part of our code in Chrome to exploit the first one, 2019-13751, uninitialized data read in SQLite. And we first using the 13750, which is a defense in depth bypass in SQLite to create a malicious table. Then we put the code leaking as many data as we can. Based on the leaked data, we try to calculate the address from the heap data. Because the heap that the FTS queries are used are fixed during every run. So basically, we can expect to reuse the same heap every time. The heap will contain some old function pointers like the VF table or page stress of SQLite 3, which is used by other functions before. This is because there's almost no one using the dlmalloc, and this heap is only used by SQLite itself, so it's very stable to exploit this. After we get the address, we can pass the base address to step 2. And this is our final POC of code execution part. The base address of function exploit is to get from the previous step. And we first set the malicious data into the FTS table, and then we try to create hotspots on heap and place the fake objects there in the for loop. You can see we call the select replace hex 0 blob many times. This will create a hotspot for us to put our fake objects there. And the last one, after merge equal 1, 2, the vulnerability is triggered. And here, first we will try to overwrite the SQLite 3 config. We found a global space before SQLite 3 config, which is not used by anybody. We put the rob gadgets there, and we will override SQLite 3 config also. So I got a snapshot of normally how does it look like in Chrome, and then set the data to the same value as the normal time. The only thing is I need to modify is SQLite 3 memfree and SQLite 3 realloc and xinit, xshutdown. The xinit and xshutdown are two function pointers. They accept one parameter, but normally no one will call it, so it is okay to set them to other value. I overwrote the SQLite 3 memory free to assembly return, so it will literally do nothing. And the realloc points to xinit. Xinit and xshutdown points to the first rope gadget. You know that realloc takes two parameters, and RCX is the heap address, and RDX is the required size. So we can have RCX, which is a heap buffer. And usually after the arbitrary write, there will be a realloc, and the address is the start address of the rope gadgets. This is a part of training rope gadgets. The rope 1 is called with a known RCX. The RCX is pointed to the first byte of the shellcode, and the figure 1 shows the value of the shellcode part, and the figure 2 is the rope gadgets part. We found that gadget, we can use it to control RDX, RAX, RCX, and jump to RAX finally. Yeah, we can control a lot of registers, but the content of RCX is controllable, so we simply put the value to offset 0x3, 0, 20, and 28 in sequence. The RAX should point to rope gadget 2. The rope gadget 2 stores the current RSP value, so we can restore it back to correct value after the exploitation. The rope 3 is a stack pivot. The rope 10 will jump to virtual protect to set the global data to RWX. Then we can run our shellcode. We have a bunch of knobs here because the virtual protect will write something back to the stack, so this buffer can prevent it destroying our stack. And after the loop area here, we try to call the virtual protect again to set the code page of global read-only zone to writable. After that, we can modify a read-only string navigator.appName. We changed it and set the value of it to Punscape to show that our exploit has succeeded. Yeah. Also, we need to restore the stack pointer after this step. We subtracted stored the RSP and restored it into correct value, so everything is rewind to the time before we exploited it. And since programs are expecting this to be a realloc, but we are not doing anything related to the memory, so we must return fail now to make the program think that there's some memory problem and tries to give up its operation. This can stabilize the problem. This can stabilize the program. And once our shellcode is run, we don't need to get into here another time. So we can set realloc to another code pattern that's always return fail. And the web page will not crash, and JavaScript can still run as usual. Everything's fine, except the web circle in this tab cannot work properly. Normally, the bypass of ASLR is almost 100% of success, and the success rate for the second step, the code execution, is about 16% per try. And here's a small tip. If you want to increase the success rate, you can use the iframe to visit a lot of exploit pages, which are located in different domains. So Chrome will have different process with each iframe. And we only tried once in the TAMP Cup 2019, and the result is succeeded. Yeah, and that's all for the exploitation part. Okay, and here's our conclusion on all of these works. And first, sometimes I think it is better to focus on a smaller scope of functions. The common use further can save a lot of time in programming, but it will take more time to test a specific area. So you should write a focus further, especially you believe that some area has lower code quality or there's more likely to have bugs there. And then, regardless of programming language, deserialization can be tricky. That's because deserialization often have external data from users at the input and then convert the input to an object. But it is very hard for the programmer to test all the unexpected conditions. So you should pay more attention here when you auditing the code or you are testing the program. And the last one, if memory is initialized according to the user input, you should remember to always zero it before use. It doesn't matter if the memory is based on stack or heap or anywhere. To remember, always clear them, so the attacker won't get useful data from the uninitialized data. Yeah, they may often have some sensitive things like the function pointers or any pointers or even the encryption keys or something. Yeah, always remember to zero it before use. Yeah, that's all for my talk, and thank you very much for your listening. And also, because this is a pre-recorded video, so I can't answer your questions now. But if you have any questions about this talk, please kindly contact my email. It's leon@gmail.com. Yeah, the email address is the same as my talk. Thank you again, and stay safe. Bye.